Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome everybody again to another episode of our show. Today bringing you another really awesome guest involved in science and technology, designed to create a better, safer tomorrow for all of us. Today on the show, we are honored to be joined by Dr. Paul Jaffe, who is a program manager in Darpa's Tactical Technology Office. There he oversees what's known as the Power Project, or Persistent Optical Wireless Energy Relay, which ultimately aims to revolutionize energy distribution through airborne wireless power transfer, enabling so-called high power beaming, really radically reshaping how we think about our relationship with energy, unlocking new power opportunities from energy-starved communities to space colonies and everywhere in between. Prior to Darpa, Dr. Jaffe spent 30 years as an engineer and researcher at the United States Naval Research Laboratory, and at NRL he held major roles working with dozens of space missions and breakthrough technology for NASA, for NOAA, for Darpa, for the Office of Secretary of Defense, as well as other military services and sponsors. Dr. Jaffe served as coordinator for NRL's seminal studies for the military applications of space solar, as well as an editor of the study group's final reports, and was the principal investigator for the groundbreaking research involving the development and testing of initial modules for the conversion of sunlight into microwaves. He's also an accomplished author. His book just came out, Power Beaming, History, Theory, and Practice, in 2024. He did his bachelor's in science electrical engineering from University of Maryland, College Park, went on to do a master's in electrical engineering at Johns Hopkins, and then graduated and then did a PhD in electrical engineering at the University of Maryland as well. A lot of really cool themes to get into today. Much longer bio will be in the show notes. But Dr. Paul Jaffe, thank you so much for taking time to come on the show today.
Ira, it's a pleasure to be here. Thanks for the kind introduction.
Yeah, no, it's great having you. I really look forward to doing this episode with you. Before we get into all cool things that you've been doing the last couple of decades in space and energy and everything in between, take a couple minutes to just tell us a little bit more about your background, because it seems like you got into electrical engineering sort of fast and furious from the very beginning. Just tell us a little bit more about yourself and your background, if you would.
Yeah, well, for as long as I can remember, I've been interested in both space and energy. I remember as a kid, we would take road trips and we would go up 270, Interstate 270 in Maryland, and we would pass the SolarX facility, which has been gone for many, many years. But it was this weird wedge-shaped building with all these solar panels on it, and that struck me as unusual and interesting, and that's kind of stayed in my head for a while. And just the whole idea of solar energy being almost magical, right? You have an object and light falls on it and electricity is produced without any fuel or anything. Kind of amazing. And I also grew up during the era with the space shuttle, and that was something of great interest. So space and energy have been kind of recurring themes throughout my life. And I actually, when I started as an undergrad, I was actually an undecided major before I faced reality and realized that I wanted to do engineering. So those decisions certainly guided by this pervasive interest in both space and energy fields.
And before, obviously space solar and power beaming and some of these themes that we get into came on the scene, you've been involved in a lot of other really cool projects, just looking through, some of your biography here, things like something known as SULI, a special sensor ultraviolet limb imager, which sort of took a look at sort of space weather and geomagnetic storms and solar flares. You're involved in something called Space Wire, which had to do with sort of high speed but low power communication dynamics on the space station. Even these texts, I mean, GP Sandhu, who we had on the show about a
Yeah.
year ago, I know you published with him. A lot of really cool things that had nothing to do with power beaming. Talk a little about some of these early projects, because they're each one is individually as cool and cooler than the next, but sort of tells a story of, again, who you are and the type of really cool things you've been doing.
Yeah, for sure. Well, some of this I have to give huge props to the Naval Research Laboratory, not only as a fantastic place to work, but also because they were able to support a lot of my education, right? So there's great programs in the government for what they call shortage categories. So for engineers in particular, if you start as a an intern or an intern or a co-op student as I did, they will help support your tuition and they will also guarantee you a job upon graduation. And this was a great opportunity for me because there was tons of fantastic work going on at NRL as there is still today. I started there actually in the radar division before moving to the remote sensing division before moving to the spacecraft engineering department. And there's just this whole spectrum of really groundbreaking, fantastic work they do. You mentioned several of them. There's sensors for measuring the atmosphere, the ionosphere. It turns out a lot of people don't know this, that like during the day the sunlight shines on the upper atmosphere and it actually like causes chemical reactions up there and they persist onto the night side, and you can actually get like an ultraviolet glow from the ionosphere, which you can measure and determine a lot of things about atmospheric viscosity and the total electron content, which affects how much you can bounce radio waves off the atmosphere, and it affects long distance communication over the horizon radar. So I got to be involved with a sensor for that. I got to go out to quite a number of launches on the West Coast and the East Coast. Got to actually crawl inside the payload fairing of a rocket shortly before launch to like do the final arm plug connections and things and make sure that everything was right with the sensor right before launch. So a lot of really great adventures at NRL and across a whole range of fields, right? So there's the space weather. We also did a microwave imager sounder, which was for measuring emanations from the Earth in the microwave spectrum, which can be also used for all kinds of things. So there's a satellite that I believe is still in operation now, probably, oh gosh, it's probably coming up on 20 years now, WinSat and the successors to WinSat that we worked on. Everything that's not at absolute zero actually emits like a low level of electromagnetic energy, often in the microwave spectrum. And by looking at that and looking at the intensity of that and the spectral content and the polarization, you can determine all kinds of things about the Earth, including being able to measure the wind speed on the ocean surface from space and being able to measure soil moisture content from space. So all these things that seem like that you shouldn't really be able to do them, it is possible to do with the right kind of space sensor. And that was a formative part of my career. I also got to work on a mission called TACSAT-1. This
Mm-hmm.
was thinking back now a little ways ago because it was around the centennial of the Wright brothers in 2003. We actually, before SpaceX was at the level that it is today, Elon Musk actually came to NRL. He said, "Hey, we're going to try to launch this rocket, the Falcon 1, on the occasion or prior to the occasion of the Wright brothers' centennial of flight in December 2003. Can you have a satellite that we can launch?" And this was like less than a year before that. And at the time, the whole faster, better, cheaper thing was still not as much of a thing, I would say, as it is today. But we were able to put together a TACSAT-1 spacecraft and had it ready not in time for the Wright brothers centennial, but less than a year from when we were charged with putting it together. The rocket wasn't ready, and then for those that know the early history of SpaceX, they went through quite a few launch failures before being successful. So that was kind of its own saga. But yeah, another exciting moment as a young engineer. I looked forward to spending 12, 16-hour days and working weekends to like get my part of it to work right to the neglect of other aspects of my life.
Very cool. No, really cool. Um, yeah, so again, speaking of a Naval Research Laboratory, obviously a lot of things that you were working on. Come 2009, a very important report which you're involved in is presented. It's entitled "The Space-Based Solar Power: Possible Defense Application Opportunities and Our Contributions." And sort of this is sort of where, again, the initial principles and concepts of space solar and sunlight to microwave conversion happens. And again, it's a very complex report. Sort of the simple part up front that I was able to digest. Okay, we got a major fusion provider in the sky. It's always out. It's always shining. There's no clouds up there. And ultimately, if we can capture that power and send it places that maybe it's difficult to get, or we don't have photovoltaic arrays, a lot of really cool things we can do with this principle of space solar combined with power beaming. And then the rest of the report is all about really complex things like advanced thermal management architectures and atmospheric drag on the satellites and space robotics and all the other cool things we're going to do to make this happen. Very cool report. Take us to 2009 now, because I'd love to hear sort of the genesis of sort of who was it. You was it whomever? Say, I got an idea, and we're going to do this and put some resources into this really cool concept.
Yeah, there's kind of an interesting chain of contingencies there. So certainly solar power satellites are something that people have been talking about for a really long time, right? So you can look back to Isaac Asimov's 1941 science fiction short story called Reason, which features a solar power satellite. And there's a lot of work done in the 60s and the 70s. The Department of Energy and NASA in the 70s did quite a lot of studies on this. There were compelling power beaming demonstrations that were done back at that time, including one which the power level record still stands today. That was done in 1975, where they sent 34 kilowatts over about a mile. And honestly, it was only relatively recently that the record was beaten, but about a year that beat that distance record quite a lot. But what led up to that 2009 study was actually a study that had come out shortly before it from the National Security Space Office under the instigation of John Menkins and Pete Garrettson and Paul Damphus and Coyote Smith and other folks that had gotten this, I think it was like the phase zero feasibility study or something along those lines from the National Security Space Office looking at this. And this was in turn driven by the fact that we've had these engagements in the Middle East. And one of the key challenges for those engagements was energy resupply, right? So we had many circumstances where the convoys of trucks that were carrying the fuel, and not just fuel, but water and supplies and everything else, but principally fuel, were very vulnerable to attack. And we were sustaining a lot of casualties just by the requirement to continue these energy logistics operations. So the thought was, well, if we could somehow get the energy to where we need it without having to move this fuel, without it taking so long, without putting these people at risk, that would be a real game changer. And that was one of the driving motivations for that 2007 National Security Space Office report. That got a flurry of media attention, and then folks at NRL noticed it. I think it was covered in Space News. I remember walking into my boss's office at the time, Mark Johnson, with this clipping from Space News, or maybe it was the other way around. One of us showed it to the other, and NRL was like, "Okay, is this just nonsense, or should something be happening here?" So we got the top folks at NRL from various different divisions to get together to do this study funded by NRL internal funds to really look at this. And we went through kind of what I now recognize are these usual stages of disbelief for this technology, where it's like, 1/r², right? Any energy you try to send is just going to spread out. And this is dumb and pointless. But as we looked into it, it's like, oh, well, maybe not, because these are actually focused beams, and we're talking about apertures that are large enough that it is possible to focus over these stupendously large distances. So we looked at that. We modeled a couple like very high level concepts of operations and said for some of them, yeah, no, this might be possible, and other ones like, yeah, no, that's probably distant future stuff that is much less likely. And the takeaway was, yeah, no, there might be something here. There's a huge uncertainty as to whether there's any chance of economic feasibility for using energy supplied this way for like the utility grid. But for DoD, we were already paying in many circumstances multiple times what a typical utility ratepayer would pay in the States, and
Mhm.
sometimes like a stupendous amount higher than that, right? Like not just 10 cents a kilowatt hour, but like $100 a kilowatt hour. So when you start talking about numbers like that, it's like, well, maybe doing something like this from space isn't so crazy. So we looked at, like you referenced, some of the subsystems and the technologies that would be needed to make that more feasible or to understand where the challenges were. And one of the things that we arrived at was the integrated energy conversion aspect of it. So by that, I mean, for the concept that was kind of popular at that time was called the integrated symmetrical concentrator. It's the idea that for solar power satellites collecting sunlight in space and beaming it to the Earth, you would have a large solar collector, you would convert that solar energy into microwaves, and then you would send those microwaves down to the receiver on the Earth. And because you'd be converting a lot of solar energy, you wanted to avoid as much as you could, like having to concentrate it through some giant wire that was going to have stupendous amounts of current flowing through it. So we looked at what was called the sandwich approach, the idea that you
Mhm.
would do the sunlight conversion on the top, the conversion to microwave in the middle, and then the bottom would be the antenna. And
Mhm.
by doing this, because you're already going to have a large solar panel and you're already going to have a large microwave transmitter, you've made these two large areas you know you have to have part of the same thing. And you just have to make a conversion element to build these big apertures from the sandwich module. So after that 2009 NRL report, we proposed research to say like, hey, well, let's make one of these sandwich modules and see like what the limit is, like what is truly the state of the art, what are the real challenges, what are the opportunities here. And that actually turned into my doctoral research
Right.
because I had it as an NRL based program effort, and I approached Victor Granatstein at the University of Maryland and said, "Hey, I'm going to be doing this research at NRL. Does this make sense as like doctoral research as well?" And we kind of went back and forth and looked at how it might make sense and made some tweaks, and that ended up being the basis of my doctoral research and my dissertation some years later. But we did that, and that did ultimately, as I imagine we'll get into, fly in space on the X-37B space plane in
Mhm.
2020, and that was kind of a long, winding road. But that 2009 report was the genesis of a lot of this. It was shortly after my first exposure to the idea of power beaming and solar power satellites, and it did a lot of framing for what the challenges were, a lot of the separating of the wheat from the chaff, because with solar power satellites in particular, there's this somewhat polarized spectrum of folks where there's some people who are really, really into it and see it as kind of the only salvation of humanity from an energy standpoint. And then there are people who are really, really against it, who see it as like the dumbest thing ever. And my finding then and since has been that the truth is likely somewhere in the middle, and that it depends a little bit on what are you trying to use it for and what are the assumptions you're making, and can you realistically project into the future, like what the specific power of solar and microwave conversion and optical conversion is likely to be, and how will you use this, where you'll receive it. So it's a classic kind of it depends situation, but it's easier for people just to be like, it's awesome or it's terrible, right?
Right. Right. No, it's and again, this sort of feeds quite nicely because you mentioned, yeah, I mean, your 2013 thesis, and we'll put a link to this, is entitled "The Sunlight to Microwave Power Transmission Module Prototype for Space Solar Power." And in the dissertation, is this chart, which actually is it's in your book too, which is really cool, and it sort of shows the different segments of the process, efficiencies, and so forth as you go along the way. The dissertation, as you mentioned, is sort of the first three steps there. So photovoltaics, DC, the radio frequency conversion, and the initial antenna. Any interesting? Yeah, the whole part of the solar sandwiches and the tile and step methodologies and all that were kind of cool. Most of it went over my head, but any interesting things just in general that you learn in terms of what's best in terms of these sandwich configurations? I know there's different types of chemicals, gallium arsenide and all these interesting types of glasses and encapsulants. Any top line stuff in terms of those three steps, sort of takeaways, and at the same time, what did you learn about? Because we're going from a frequency, we're converting it into energy, but then we're resending it, and we'll get to sort of where it goes later. But through this first antenna, what did you learn about? Because the efficiencies are listed here from 2013. Talk a little bit about that for those maybe only familiar with, hey, okay, is the sun? It's hitting these solar panels down here that we have on the ground. Learning sort of in those first three steps that you came away with in 2013 per that.
Yeah, one thing is people really gravitate towards efficiency.
Yeah.
Or always ask about efficiency, and I think the reason for that is because it seems like something that's important and it's something that is pretty easy to understand. But the fact is that efficiency, while important, is not like the thing of paramount importance in actually most situations, right? So when you go out and you buy a car, your first question is not like, well, how efficient is this car, right?
Right.
You have other needs and other requirements that you're trying to meet before the efficiency of the car being a consideration. If it was like the main efficient or the main consideration when people bought a car, like everybody would be buying EVs because EVs are much more efficient than gasoline cars. The cost financially to get that in space is driven by the mass. So we looked actually pretty carefully, and I'll try to tie this together because it's not too bad once you have all the pieces. Is there's four things that you can kind of look at to determine the cost of electricity from space solar, whether it's for defense purposes or whether it's for the grid. And that is the cost of getting stuff into space, which you can express like per unit mass, the cost of whatever it is you're going to be putting into space, which you can also express like per unit mass. So each of these could be like dollars per kilogram. Then there's how long it's going to be up there working, and you want that to be a long time because that way you don't have to replace it and you can get as much energy as you can out of the whole system over time. And then the final and fourth thing is the specific power, or I guess more specifically, the mass specific power. So this is the watts per kilogram. So if you can make the amount of power that you get down per unit mass super high, even if it's inefficient, you may still be able to close a cost case. So efficiency is really kind of like a proxy for specific power, but because specific power is a little more abstract, that's not the thing that people look to first. So when we did the sandwich module prototyping, we made a real point of like measuring the specific power and seeing what trends might be needed or what projections could realistically be made for increasing that. And to be frank, the specific power of our sandwich module prototype was not fantastic, but it showed kind of like the starting point, and it gave us a basis for projecting where it might need to go in order to get the cost down.
Done. Done.
And you mentioned the tile and the tile and the step module. We did a patent for something called the step module, which was a way to deal with the thermal control, right? So when you have inefficiencies, that gets expressed as heat much of the time, right? So like, and one thing worth pointing out, for sunlight conversion, inevitably the least efficient part of the whole system is likely to be the photovoltaics if you're using solar cells for conversion. So today, if you buy like the really good solar cells designed for spacecraft, multi-junction, 3-5 cells, they'll be at the cell level like low 30, mid 30% efficient, which is great, right? Like that's a lot better than a typical silicon solar cell that you would use for terrestrial purposes. But that's still like 30%, 30 or 35% efficient. That means that you got like 60+% of the energy going somewhere else, and most of that is to heat. Some of it's reflected, a small amount is reflected, but a lot of that is going to heat. And that means that you have to figure out like, well, what are you going to do with this heat? Because your system is just going to keep getting hotter and hotter, and components don't like to be hot because they start to become more failure prone, less reliable. So one thing we did with the patent we had for the step modules is we said, if you are assuming this like flat array of sandwich modules, you only have two sides. You have the top and the bottom, and that is where you can radiate the heat away into space. By making the step module, we added a third dimension where now you could still make a surface, albeit now it looks more like a cone or a variety of different shapes. Like we had like a kind of like uh, corrugated potato chip looking array, and there's a bunch of different things you could do. But it means that you create extra area that you can use for radiating heat away. And now you can operate it at a higher concentration. Like one thing that the sandwich module approach requires is a way to track the sun and where you're sending the energy on the earth at the same time. So it requires like either like a reflector or some other means to help with the energy redirection, since you're doing all the conversion in this flat surface. So, and the same would be true even if you made the sandwich module array out of these step modules instead. So, but yeah, so that was part of what we looked at. Like, there's no getting away from Stefan Boltzmann law, T to the fourth, heat power radiation. So that was an important aspect of that, and that's something that is a challenge for most spacecraft, and anything where you don't have like super high efficiencies is going to generate heat, and you need to give thought to the thermal dissipation scheme.
Got it. And as far as the beaming side of it, because then again, after those first couple steps, there's the process of sending things down and capturing it again. And I've heard previous interviews that you've given, talking about three things. One, microwaves, which can be caught via various antennas, or this rectifying antenna concept. Lasers, which require sort of different types of photodetectors and receivers. And then sort of the third option I heard you talk a little bit about was just, sending something, I guess, not as precise as a laser, but sort of waves of light that actually would hit a traditional solar array on Earth somewhere. Take us through some of that, because I think this is the one part maybe people that are less familiar with this type of technology may have a little trouble wrapping their heads around, but love for you to walk us through some of what you envision here.
Yeah, for sure. Well, and maybe the place to start for that is electromagnetic waves are surprisingly good at moving energy around, right? We don't usually think of them in those terms. We usually think of wires, but the sun, the sun is about 93 million miles away. If you wanted to get solar energy from the sun using a wire, like, it's not really going to work, because a 93 million mile long wire is going to have a lot of resistance, and it's just not, it's like a non-starter, right? So, but we get the sunlight here, and now, to be fair, like, the sun is like a thermonuclear reaction and is sending energy in like all directions, not just towards the earth. So it's got a lot of energy to give, but the energy that it is giving like gets to the earth pretty well. You could also look at just like stars at night, right? Like, we see stars that are mind-bogglingly far away, and yet you can still see the energy from that with naked eye. That energy, of course, is coming through electromagnetic waves.
Yeah.
So having established that electromagnetic waves are a way to move energy, we can look at the limitations that we might have in our typical terrestrial context for trying to use them to do this. So the atmosphere scatters light. There are in the atmosphere what we call these different windows. There's two windows, the radio window and the optical window, where electromagnetic waves travel more easily, are less absorbed, less disturbed. So that leads us to these modalities that you described. So the microwave is longer waves. So this is going to be typically from like 2 gigahertz up to 10 gigahertz, or maybe even as high as 20 or 35. And in some rare cases, maybe W band, maybe 94 gigahertz. So to do power transmission in this regime, you have to have a way to generate the microwaves. So this might be like your microwave oven at home, or your Wi-Fi base station is a microwave generator, even though most people wouldn't think of it in those terms. Obviously, the power level is much lower than your microwave oven. So that generates those waves, and looking at 2.4 gigahertz, that's like a wavelength of like 12 centimeters. And then to convert it back into DC, you use an antenna and a rectifier. The portmanteau way to or word for this is the rectenna.
Mm-hmm.
And these are quite easy to make. Even we had the Darpa Family Day here recently. We had 4-year-olds making what we call lectennas, which is a rectenna with an LED, and you get the right kind of diode and an LED, and you twist the leads together, and it just happens to be close enough to the right distance that it's great. You hold it up to your phone or your Wi-Fi router, and it lights up, and it's like, oh, wireless power is real. So there's there's a couple ways to do that. As you go up in frequency, you have a benefit in that the antennas you need to keep the beam focused get a bit smaller. This is just a matter of the physics of electromagnetic waves and focusing and the uncertainty principle. So for shorter wavelengths, you can get a focus beam with a smaller aperture. This drives us potentially into the optical regime, where the wavelengths are way shorter than they are for microwave or for radio waves. And it does change kind of how we generate those electromagnetic waves, and it does change also how we receive them and convert them on the other end, like you were describing. So for very directive optical waves, we like to use a laser, because laser light is coherent and gives us already a beam that doesn't diverge very much. And we can use optics to kind of manipulate that to suit whatever situation we're in. And on the conversion side, it's very similar to a solar cell that converts sunlight. The key main difference being that laser light is monochromatic. It's not spread spectrum. It's not broad
Mm-hmm.
spectrum like the sunlight, where a solar cell needs to try to convert all the colors that we can see, and then as much of the infrared in the sunlight that we can't see, to try to get the electricity from that. Because the laser is just generating energy at a single wavelength, you just need to convert at that wavelength really well. And that gives you the opportunity to have cells that, instead of having to try to deal with this whole spectrum, can convert that one single wavelength really well. And we do this by matching it to what's called the band gap of the material. So if you pick a specific material and you know that it's going to convert really well at, say, 1 micron, you then illuminate it with light that is at 1 micron. And there have been demonstrations and devices that have been created that have shown conversion efficiencies much higher than even like the best experimental solar cell efficiency. So I mentioned like mid
Yep.
30% for like the space cells, and probably like 20-ish% for like your kind of garden variety silicon solar cell. The research cells for solar are like almost at 50%. Like if you look at the National Renewable Energy Lab, they have a
Mm-hmm.
great plot for this of research cell efficiencies. They're like at like 47 something percent. I guess I haven't looked at it recently. So, but almost 50%.
Mm-hmm.
For monochromatic light conversion, it's way more than 50%. They've
Okay.
been shown upwards of 60, and if you like bring them down to like really cold temperatures, even as much as like 70 and 80. So the efficiency of converting monochromatic light is a lot higher, or certainly can be a lot higher than for solar cells. And I guess I should mention for the rectennas, those also have shown very high conversion efficiency. Typically, at the lower frequencies, the conversion is better. Even in like the 1980s, they were showing like better than 90% conversion efficiency for rectenna elements. This all like is at the element level. So if you start making like a big array of these things, you do have some losses from how you combine things and how you put them together, and any parts of it where energy might be like passing by rather than getting converted.
Mm-hmm. Mm-hmm. Yeah, I mean, it's again, it shows the and I appreciate you taking your time to walk us through this, Paul. But it's important to show in essence where we're going next, because obviously you come from NRL, you're Darpa now, and as mentioned at the beginning, that it's called the Power Program, Persistent Optical Wireless Energy Relay, that you continue to champion and progress. A couple of major milestones I'd love for you to talk about. One, which was back in 2023, which was something known as the SWELL project, the Space Wireless Energy Laser Link, and this was the successful 100-day experience with the space station, and then more recently, what is known as PRAD, or Power Receiver Array Demo. This was just a couple of weeks ago when you announced a rather successful transmission. Walk us through a little bit of what's happening in the last couple of years, because again, it shows the not just your dedication to continuing this, but you're really taking it a couple of orders of magnitude further now. So it's quite exciting.
Indeed, yeah, and there's an important turning point here that I need to make sure I convey, and that is in 2016, the U.S. government held the Defense Development and Diplomacy Innovation Challenge. And this was something where my colleague Pete Garrettson had like contacted me, and he said, "Hey, Paul, we should really put in something for this." And I was really busy at the time, and I kind of like put him off a little bit, but he was persistent, and I was like, "All right, fine, let's do this." So we submitted like an abstract, and out of some number of hundreds of applicants, they like picked us for the semifinals, and we went to the Pentagon and we made this pitch. And coming out of that, we were like one of the, I think, 4 to 6 finalists, and then at the Department of State, they held like the finals, and they had all these generals and political appointees and undersecretaries to watch this. Is quite a big production. Actually, you can see the presentation from this. The video is online. They had an introduction from John Kerry, and I think from the SecDef at the time. But we pitched this idea of space solar, and in the audience at the time was the uh, Deputy Assistant Secretary of Defense for Operational Energy, Amanda Simpson, and she apparently saw this presentation and she's like, "I'm going to do something to make this happen." And she decreed, I believe, I may have someone want to verify some of this history for me, but I believe that she said, "All right, for the operational energy capability improvement solicitation, we are going to explicitly ask for power beaming," right? They called it far field wireless power transmission, I think, at the time.
Mm-hmm.
It was that was like, I think, a key turning point for the United States, where there was actually like a really concerted effort to say like, "Hey, is this technology going to fly? Is this going to be worth it?" And starting in 2017, under the leadership of Ruth Ann Darling, the OSD Operational Energy Innovation folks like took a real critical look at what needed to happen and where the shortfalls were and how this could be tied to something that would have DoD relevance. And that focus has been essential, I think, in getting us to where we are today. So you mentioned Swell, which was funded through Operational Energy Innovation. They also like laid the groundwork for a lot of this. Like, so the one you made reference to, PRAD, which we did this year, built on the progress that Operational Energy Innovation fostered through programs like Scope M, which was a microwave power beaming demonstration conducted by the Naval Research Lab, where 1.6 kilowatts was sent over a 1 kilometer distance, and a parallel program called Scope O. These were acronyms for Safe Continuous Power Beaming, M for microwave and O for optical, that showed 500 watts delivered over a kilometer. So we've done these terrestrially. We realized that there are so many applications for space on the moon, in orbit, elsewhere, that we should see what some of the challenges might be for establishing optical power beaming links in space. And this actually started kind of as a COVID project. I guess, amused and embarrassed to say, where, March 2020, they just said, don't come to work, right? You're working from home now. It's like, okay. So one of the great things about NRL is they have labs everywhere for doing things. So now we're at home, like you can't go to the lab. So I was like, all right, well, I guess I'll like start building stuff in my basement. So like during those first months of COVID, I was like, well, I've got these lasers, and I got these solar cells, and I started playing around in my basement making like these little optical power beaming links. And I was thinking, it would be pretty straightforward just to do something like this in space, like in a compact, like quick and dirty way. And we pitched that, and to our surprise, like it got picked up almost immediately because I'd been doing things with the space test program for a while, and usually it was a pretty long process. But we came up with this pitch. I'm not gonna say overnight, but it was pretty close. And they're like, "Yep, here we can put you on STP-H9, and it's got to fit in this size." So we're like, "Okay, we'll make it fit in that size." And we built up Swell really on a shoestring. Kudos to my coworker and colleague Krista Puma for helping to run that. He also was instrumental for PRAD or for PRAM, the photovoltaic RF antenna module that was the sandwich module that flew on the X-37B launch in 2020. But Swell was basically a laser in a box with a receiver. It was like a meter and a half almost. And we had two of them, just primary and redundant, because we had a little bit of extra space. But that was how we set it up. We knew that there had not been previously, with very few exceptions, a lot of careful documentation of where the losses were in these kinds of wireless links, these power viewing links. So when we did Swell, we're like, all right, we're going to know exactly what's going into the laser. We're going to know exactly what's coming out of the receiver. We can do measurements and everything else to really make a good Sankey diagram that shows like what you started with and what you ended up with and where stuff got lost along the way. So we did that, and there's a paper for that. I don't know if you've seen that. We presented it at the Optical Wireless Power Transfer Conference. My colleague Elias Wilkowski, I believe, presented that.
Okay.
But yeah, so that's how we got to doing this first instance of laser power beaming in space, and it was all enclosed in a box. Like this wasn't like between satellites or anything. It was all on the space station in a long, skinny box as part of SDPH9, and it operated for months and months. So it probably has like the longevity record for a power beaming link being on continuously for a long period of time. And we got a lot of great data out of that. There was a lot of question like, well, what's the space environment going to do to this? Like, will the optics be subject to like radiation damage, or is there some other thermal problem that might crop up? But we showed that it could be done, and I think it's a great place to build from. Like in itself, it was like more of a pretty fundamental demo. I would call it the hello world equivalent of for optical power beaming in space. But yeah, it was quite successful.
And obviously, based on the success, these recent successes, Power Phase Two is happening. I know just it was a couple of weeks ago that you held Industry Day to again further talk about these concepts, bring together researchers, maybe industry, look at sort of again the different pieces that have to happen. Can you tell us a little bit about how Industry Day went? Not specifically who showed up, but the types of folks who showed up, and sort of what the general feel of things were, and the excitement around Phase Two, because it's clearly kind of exciting
Yeah, for
time.
sure. So phase one, we had folks look at basically, is this even possible, right? We had a lot of technical questions about whether or not the pointing could be accomplished, the pointing and tracking could be accomplished, whether the subsystems were at a level of maturity where it would be even possible to get an integrated system that could do this, that could get close to the mass that we needed to make this feasible. And phase one showed that that was possible. We had performers that got to the preliminary design level and showed that it was possible. We also realized along the way that for phase two and phase three to be successful, we're going to need to have some kind of receiver, right? Like the initial solicitation for phase one by design, and I think sensibly so, had people focus on the relay. But we realized like, hey, for phase two, like we're gonna have some kind of receiver. So we decided to do a small risk reduction effort called PRAD, which you made reference to earlier, the power receiver array demonstration,
Right.
where we put out just a quick solicitation. We said, look, we've got 350K and 3 months. Who can build a receiver for this? And we actually had like a really robust response to that. And we had down select for that. We picked a performer. That led to the demonstration that occurred just this past March, April timeframe that did set the record for power beaming distance, almost as a byproduct, because the main thing we were trying to do is say, hey, yes, we do have a receiver. So when we move forward with phase two and phase three, like it's not just going to be like dumped into like a calorimeter or something. We'll have an actual receiver we could use. So we worked with a company called Teravec that built the receiver,
Mm-hmm.
and that we spent a week of testing out at the High Energy Laser Systems Test Facility at White Sands Missile Range in New Mexico. We tested first at like about a kilometer, at 2.4 kilometers, and then finally at 8.6 kilometers. And we were able to get out of that receiver more than 800 watts at 8.6 kilometers away, which far and away the longest distance and the highest power level simultaneously for any power beaming demonstration. And that helped, I think, drive a lot of interest in the industry day. And we had a packed house for industry day, a lot of interest, a lot of folks come to that, got a number of abstracts, and I won't talk too much about where we are now because we're still in the midst of that process,
Sure.
but we are looking to move forward with phase two. And yeah, hopefully, so the goal for power is to make a network for optical power beaming so that it's not just like a point to point thing, right? So you can think of like communications networks started with like the telephone with hey Watson, come here, I want you, as like a point to point. And now it's like the internet where you can connect with anyone and everyone through a variety of different paths, and it's a robust, resilient means of moving information around. If we can do the same thing with energy wirelessly, that will be tremendously powerful because it means that if there's a changing need, energy could be redirected quickly. And the relays that we're making for power are the key to enabling that. So with phase two, we've asked folks to build a subscale relay, so smaller than we would expect would be needed for an operational system, to show that the three functions that are required for this, the ability to redirect a beam, to correct for atmospheric aberrations, and to be able to harvest some energy from that beam, can all be integrated into that single package, show that that works, make the case that we should then move on to fund phase three to show the stand up of this network capability.
Mm-hmm. Mm-hmm. And just again for putting things in perspective of where you're going with this, and for viewers of our show, we've done several sort of directed energy technology shows, profiling, the Lawrence Livermore, the inertial fusion experiments, which those lasers in the megawatt range, some of the stuff at the Pentagon in terms of what they're doing in the high kilowatt range. Obviously, we're coming along here, but what are some of again the goals for whether it's a couple of years out, whether it's where do you see this, the curve going on this? Because clearly, obviously, doing this fusion experiment at Lawrence Livermore a little different than, hey, we got to supply some power over here to Eau Claire, Wisconsin today.
Mm-hmm.
Walk us through some of sort of the, I don't call it the dream sort of expectations here, but where this potentially ramps up, and how it ramps up, because again, we've heard some of these wattage numbers.
Yeah,
Love to just get your perspective on sort of where on the spectrum we are, and then where we're headed with this.
for sure. Yeah, and I think it's worth noting the reason we're doing this at all is everything that we do, like as people and as a civilization, with very few exceptions, is underpinned by energy, right? Like we take energy for granted. DoD takes energy less for granted, but it's still like seen as being in a supporting role when it is kind of like a critical enabler, right? So just like in the Middle East conflicts where we realize like, oh, we have these vulnerable fuel convoys that are creating problems with their cost and vulnerability. And this has been a theme, like it's not just from like the 2000s, right? You can look at like the Ukraine war and how it appears that Russia thought they could just roll into Kyiv in like a matter of days, and one of the reasons they couldn't was because their resupply convoys could not make it where they thought they could make it. You can see how this continues to be an imperative and a point where there is tremendous vulnerability and likely opportunity if those vulnerabilities can be overcome. So with defense systems, there is for sure a trend towards autonomy. There is a trend toward small attritable systems. These systems still require energy. So if you now have a circumstance where instead of having a convoy that's bringing not just fuel, but water and food and spare parts and ammunition and what have you, medical supplies, if you instead have a force structure where you have small attritable systems that just need electricity, now being able to move energy wirelessly over long distances in short periods of time becomes extra valuable because you may have replaced what used to be a complicated, cumbersome, diverse resupply ecosystem with one thing that you can deliver at the speed of light to a range of locations with great flexibility and resilience. So I know that's not maybe as concrete as an example as maybe you're looking for, but hopefully this illuminates kind of the sphere of possible outcomes that we could have. And certainly, I am very interested in particular in how this can also support like disaster response, right? So we've seen, unfortunately, in this country and across the world, like many instances where a natural disaster hits somewhere and like people are in trouble. And one of the things that is key to enabling an effective response is having access to energy, right? So like if you have a flood or a fire or something else that routes the existing energy infrastructure, the ability to say like, well, that's okay, we just need to get a receiver there and now we can send energy, that would also be very powerful to support the response and the recovery efforts.
Well, obviously we're talking about power, we're talking about energy. Obviously, energy plays such a crucial role in all 8 billion plus of our lives. Say a couple words about that, because clearly here you're dealing with a technology that ultimately, when it's developed to its full capacity, has the ability to really change things. And a sort of a geopolitical perspective, I would just love your input and thoughts on this matter, because it really is rather earth-shattering in that context.
Yeah, indeed. My friend Michael Bloxson likes to think of these terms as concerning bits, atoms, and joules. These like three things can kind of like crystallize like those quantities that are necessary for like human activity, right? So, and it's of course proxies for information, matter, and energy. And energy in particular like gets taken for granted, right? So there's, I think, a maybe subtle or not so subtle opportunity for how this could really reshape even geopolitics, right? So if you look historically, as over the last century, society and civilization has grown up, there's been a tremendous dependence on fossil fuels, and we've seen how that can be like a real vulnerability if you look at like the oil crisis from the 1970s. And as we look at energy sources, like we want to think about how they are extensible, like what their benefits and drawbacks are. Obviously, with climate change, that's a major consideration. Thinking about something like space solar in particular, it has the benefit of like terrestrial solar where it's clean because you would implement it likely in an orbit or with a constellation where it would be available more or less continuously. You can treat it as being constant. And then unlike any other source of energy, whether it's nuclear, fusion, wind, what have you, because it is space-based, it gives you the opportunity to have a global distribution network. So you could think of this as being analogous for where GPS has created an environment where we take navigation basically for granted. It's possible that space solar could do the same thing for energy. Now, if that happens, there is an opportunity for a country or company that manages to master this technology and make it cost effective to effectively become like the electrical utility for the world. And if that happens, there's for sure huge geopolitical implications because now a developing country that needs an energy source might just have to like set out a receiver and pay their bill every month to get energy beam from space. There's of course plenty of contingencies and uncertainties associated with this future that I'm painting, but it's definitely worth being aware of the possibilities existence.
And Paul, for clearly we hope we have a lot of scientists, engineers, next generation Paul Jaffe's out there that have great ideas on potentially getting involved with phase 2 and phase 3, and ultimately where this is all going. How do folks work with DARPA? I mean, there are others have systems like DARPA Connect and other tools out there, but walk us through a little bit of some of the resources that are available to the public that may hear our show, might watch our show, and say, "Hey, I got to get involved in this." And what's their next steps? How do they get involved?
Yeah, one of the most profound and compelling aspects of DARPA is that people are here only temporarily, right? So it's not like you spend your career like camped out at DARPA. You typically have like a small number of years to like get in and do your awesome thing, and then you're kicked out to make room for the next person who's going to do their cool and awesome thing. So it is exhilarating and I think a tremendous opportunity to work here. And people can work here obviously in a capacity as a program manager or as part of the office leadership. And then like DARPA is an office building, right? Like all of the actual technical work gets done by our amazing performers. And the way that potential performers or program managers can approach DARPA is through DARPA Connect, as you mentioned. URL is darpaconnect.us. And that's a great place to start if you have a cool idea or you just want to learn more about DARPA and see how you might be able to contribute.
Awesome. We will put that link in the show notes. Paul, one thing I neglected to mention in your bio is that in addition to everything you're doing, you also actually teach a course at University of Maryland on sort of introduction to power beaming and space solar, and you're also sort of very active in mentoring, in not just graduate students, but K through 12. And anyway, you mentioned before that the sort of one of the open house days that you had with sort of the kids showing up and doing that stuff. I remember, I forget which one it was. I had a DARPA guest on a couple of years ago, and was talking. There was something in sort of the manual for that particular project that talked about, if you are under 12 years of age, you got to have your parents okay to come and propose for this specific project. I'd just love to hear about some of your mentoring activities, especially for sort of the younger end of things, because it's very important that we get the next generation looking at these types of technologies, interested in them. But at the same time, any kids showing up with really cool ideas for this? Because I imagine, ideas come from everywhere, and just I don't know if there was any cool little anecdotes along the way that you can share with us.
For sure. Yeah. Well, so one thing, I think it is really important to be able to make things tangible for folks. And if you can't make it tangible for kids, it probably means you haven't done enough diligence on how you're communicating things, right? So like these lectennas, I feel are great because like people don't think about radio waves as having energy that you can use for something. And telling someone and showing somebody how they can like make something in a matter of seconds and then see it for themselves, that's super powerful, right? We did actually, when I was at NRL, we had astronaut Jessica Meir on the space station do a demonstration where she like takes one of these lectennas to the Wi-Fi base station on the ISS, on the International Space Station, and shows like, hey, look, it's converting the Wi-Fi signals back to DC and lighting up this LED. So you can see that, and the fact that you can make these things quickly and inexpensively, I think, makes it very accessible. We've done that. Yeah, we've done it with, and there's been tremendous efforts, not just from NRL, but the Air Force Research Laboratory and other folks that have like really picked up the baton on this and used this for STEM outreach because you can get like a little Wi-Fi extender and use it basically anywhere with Cub Scouts or students or whatever to make these things and show it. So it's a great little STEM project. I have worked with student interns and yeah, the K through 12 in various capacities over the years, largely when I was at NRL. And as you mentioned, I do teach this course at the University of Maryland, which I've taught now since 2017, every other spring. Always try to bring a hands-on aspect to that too, to help people awake in class. And yeah, there's been a lot of creativity that you see from students that come in with ideas that are decidedly out of the box and oftentimes like really insightful. Like I remember reviewing intern applications at NRL, and one of the students had like done an optical power beaming demonstration in its basement using like an engraving laser and like a solar cell. And part of me was like, oh my gosh, that sounds really dangerous. Uh, but he did it, and it showed like kind of the resourcefulness and creativity. And now he has started his own company trying to commercialize this. So there's definitely a lot of inspiring folks in this area doing really cool things. And even within just the last few years, both on the power beaming side and on the space solar side. And I think it's important to make them distinct, right? Because power beaming can be used for a lot of stuff. Space solar is like a particular application of power beaming that has potentially tremendous promise. And we're seeing activity in both. Like there are startups pushing both technologies forward, and hopefully within the next few years here, we'll continue to see really remarkable breakthroughs with work we're doing here at Darpa and in the larger world as well.
And final thing while we have you, I just mentioned, May 29th was Industry Day. Other milestones coming up with regard to phase two that we should know about while we have you today? Any other public facing stuff that for the rest of 2025 as we get into 2026 related to the Power Project that I missed? And anything else you want to mention while we have you, please, Paul?
Yeah, well, so we're looking to get phase two kicked off here, hopefully within a few months. Obviously, a bunch of contingencies in there, and then as long as I'm at Darpa, I have like a constant stream of ideas. I'm always trying to like shape and form into new program ideas, and obviously can't talk too much about any of those yet, but stay tuned. Definitely working on those with my team and seeing where we might go.
Excellent. Excellent. Yeah, I always feel bad that you guys have to, you have that limited time there, but I guess that's the nature of the beast. But no, really very impressive work. Well, again, I'm thankful that we ultimately had the opportunity to hook up here and be able to tell your story. And I just really look forward to continue to follow what you're up to and continue to develop these technologies for that ultimately benefit all of us. Again, for everybody that is going to be listening to this episode of the show across the various podcast networks, or who will be watching on the YouTube channel. Again, you've been spending time with Dr. Paul Jaffe, Program Manager, Tactical Technology Office at DARPA on the Persistent Optical Wireless Energy Relay Project. Check out or pick up a copy of his book, Power Beaming History, Theory, and Practice. You want to really delve deep into the book because he wrote it.
I'm a co-author, so I got to give a shout out to my co-authors.
Cool. Paul, again, I want to thank you for taking the time out of your schedule to talk to us for a little while, to educate us on some really cool topics here. I mean, obviously, thank you for everything you're doing there at DARPA. And as we like to say on our show, thanks for helping to create a better tomorrow, be the type of technologies you're developing for all of us. Really an awesome story.
Great. Thanks for the opportunity, Ira. I appreciate it.
Great having you.